Hello, everybody. This is our last lecture for Unit 1. This is going to be a super important one, and there's a lot of information in here that you need to put together. And this is all about water and water vapor in the atmosphere. So you've already had some introduction to it through the Anticipating Hazardous Weather and Preparedness module. We've talked a little bit about the water in there. We're going to be seeing a lot more of it to come, but this is going to be the lecture that really establishes what you need to know. Now, next week you have a lecture on National Weather Service products, and you should be doing that next week, but that is not required for the first test. I'm going to make that test available starting on Wednesday. You'll have Wednesday through Sunday to finish that test. Here's the thing, and this is important. You must finish the test in the time allotted, and it cannot be stopped and started. So once you start it, you have to give yourself plenty of time to take the entire test and then submit it, okay? Again, the notes that you've been taking for anything that you've done in class are usable on the test. But I want you to study for the test like you're taking any test. Your notes that you've been taking and your worksheets should provide adequate information for how to do well on the test. But don't just count on the fact that you can go look it up. You need to study, think about how you want to put it together, and then that will be a lot easier to manage when you're taking this test. Now, there's one thing about a product that I want to make sure you've done, and I'm going to share my screen here for a second. Here we go. And the thing is, this is something that we have talked about once. If you go to the home page that I've talked to you about and the local weather, and if you recall this one, it's campus weather. And over on the left, there's something I want you to make sure you know. Now, we've talked a little bit about terms like FEMA, the NWS, the National Weather Service. We've talked a little bit about the Storm Prediction Center issuing watches, severe thunderstorm watches, tornado watches. We'll really get into detail. That's going to be next. But there is something that the local office puts out. It's called the HWO. If you look over here, HWO stands for Hazardous Weather Outlook. And this is a 7-day outlook. Outlooks are always kind of extended forecasts. 7 days of any hazardous weather that may threaten people in the Chicago forecast area, the county warning area, we call that. Now, this one I just happened to look at says there's really no hazardous weather. Days 2 through 7, the only thing they worry about is a high swim risk. So I'm not really going to look at that this week. But it's going to be really nice weather for here. I'm doing this lecture over the summer, so that's kind of great. But you need to know that the hazardous weather outlook is a 7-day forecast outlook to tell you what hazardous weather is expected. Excuse me while I drink some coffee. That is what you need to know for this test. The stuff on the worksheet that does NWS products, the lecture I'm going to give you on that is not on the test. But everything up to this point and this lecture on water vapor is going to be on the test. So let's start. This is the temperature and relative humidity relationships. Now listen, I think you should, if you haven't gone through this module, you need to stop and go through the module like you would do it. You need to read it. You need to go through the internal questions. You could even try taking the Med Ed quiz, but don't take the ones for grade until after you hear this lecture, because then that will give you the best score possible. Okay, so I'll show you what's important, and these are the things you need to take some serious notes on. Now, there's a lot of review here, but we're going to talk about temperature. So here's the definition of temperature. Now, a couple of you guys, I've been telling you on your lecture notes, you need to make sure you spell correctly. I know some of you are bad spellers, but everything should be in here. And if not, go look it up. Google. Lord Google knows not everything, but a lot of stuff. Okay, temperature, it says, is defined as the degree of hotness or coldness. No, temperature is the average kinetic energy, K-I-N-E-T-I-C, kinetic energy of the molecules. So there's molecules in air, and they're moving around like this. And the faster they're moving, the more kinetic energy they have. Kinetic energy is the energy of motion. So when something's warmer, they move faster. When something is cooler, they move slower. That's what you need to know about what temperature is. Now, obviously, you have Fahrenheit or Celsius. Sometimes you use an absolute temperature scale. We use Fahrenheit for most weather around here. Celsius is common also, especially as I go in the atmosphere. The thing that you want to know is, you probably should know the conversion. I'm not going to test you on the conversion. You don't need to know it now, but it's something nice to have. They talk about a dry bulb. They're just pretty much saying it's a thermometer that measures temperature. Okay? We've used the word diurnal before, so you make sure that you know that. We're going to be talking about fronts, etc., effects on fuels, and then we talk about atmospheric moisture. Now, here's where we get a little bit more in depth as far as the moisture is concerned. So I want you to go back and imagine that we've got this box of air, and in it, there's molecules, and they're moving around. Now, in that box of air, 78% about is nitrogen. 21% is oxygen. Remember, I said, what are the two most abundant gases? Nitrogen, oxygen. Okay. Some of the molecules in there are water vapor. So water vapor, H2O, right? You know that. First thing about water vapor, and we've said this before, is what? It's invisible. So we don't see it, but there's molecules of water vapor moving on, just like there's oxygen and nitrogen. We don't see them. That's water vapor. Okay? Now the question is, well, how much water vapor is in that box of air? Now, how would you tell me? Well, you could take a box, you could say, well, I know, let me count it. Okay? So imagine that I counted all of the molecules. That would be a way of answering how much water vapor is in the air. You could say there's a really big number of molecules. That seems kind of pointless, right? So now imagine that you've got a jar of gumballs. And I go, how many gumballs are in there? Now you could count them, that would take a long time. But what you could do is you could measure an empty jar and then measure the full jar and go, well, all those gumballs weigh a certain amount, and each gumball weighs a certain amount, and I could calculate how much each gumball weighs. So I could just simply weigh the gumballs. And that's the same thing of the atmosphere. I know how much a molecule weighs, and if I knew how much they all weighed, I would have an amount. So I use it in terms of mass. The problem is, watch this. I've got a collection, a box, a parcel of water vapor in air. And I said, how much is in there? And you say, well, weigh it. Okay, let's say I could weigh it. But what if I took a box this big? Do you understand that the size of the box tells me how much I have? So what that is going to end up and do for me is I'm going to create something called the mixing ratio. It's abbreviated as W, and that is the grams of water vapor. Oh, I'll spell correctly. What? No, I won't. Let's try it for the third time. No, fourth time. Grams of water vapor per kilogram of dry air. So it's how much water vapor I measure. Let's say I get 8 grams of water vapor in this box. I take that all out. What do I have left in the box? I have a box of dry air. So I weigh that dry air, and it's 2 kilograms. So I have 8 grams of water vapor, and I have 2 kilograms of leftover dry air. My mixing ratio is now 8 grams per 2 kilograms, or in other words, 4 grams per kilogram. So mixing ratio is given to me in grams per kilogram. Okay? Now, here's a weird question, but it's so easy, and you're going to get it wrong. So you want to see if you can pause me after this and see if you get the right answer. Okay, so here's the question. You should probably write down and tell me what you think your answer is, and then I'll tell you what the answer is. Of a box of air, how do you change the amount of vapor in that box? I have a box of air. How do you change the amount of water vapor in that box? Okay, now stop. Tell me what you think. And then here's how we're going to go on. Did you say something about changing temperature? A lot of you will probably have said that. Some of you will say, well, change the amount of dry air or put, make the box bigger. That doesn't make sense. I have a box. If I said I had a jar full of marbles and I asked, how do you change the marbles in the box? The answer is really easy. You put some in or you take some out. And that's the same answer for water vapor. How do you change the amount of water vapor in the box? You put some in or you take some out. I mean, that makes sense, right? So that's how you change it. Well, if you recall, we mentioned that this parcel was what we call the Vegas box, so that what's in the box stays in the box. So can I really take vapor from outside the box and put it inside the box? No, I can't. So then the question is, well, how do I change the amount of water vapor in the box if I can't put it in from outside the box or take it out of the box from inside? Okay, so I want you to imagine this. I'm going to draw a little picture here, okay? And in this box, there are molecules, okay? And a molecule, even though we can't see it, we're just going to pretend we see it, is floating around in the air, right? This is a box full of vapor, molecules of water, flowing around in the air, moving around. Okay, now, what do we call taking vapor out of the box? And I'm not talking about this. I'm not talking about taking water and putting it outside the box. It's got to stay in the box, but can I take it out of the air? And the answer is yes. And what that is I create condensation. Make that a little larger. Condensation, which is what? Vapor turning into liquid. That is what condensation is. Okay, what's the opposite of that? Evaporation, which is what? It's liquid, or liquid. Man, I'm just having a hard time spelling today. I make fun of you guys for not spelling. Turning into vapor. Okay, so those are two terms. I think, that seems kind of important that you would know that. So in other words, I've got vapor. Watch, vapor like this. And if they get together and they form a droplet of liquid water, they are condensing into liquid water. If they condense into liquid water, how much vapor is still in the box? And the answer is, well, there's less than there was before. I have taken vapor, converted it into liquid, a phase change, and in doing that, I now have less vapor. So, review. How do you change the amount of water vapor in the box? Answer, evaporation or condensation. Evaporation is taking vapor out of the air, less vapor, less mixing ratio. Evaporation is taking liquid and making it go part of the air. It's now vapor. But would I have in this box that you see on the screen, would I have evaporation able to be taking place? Is there anything in there that's left to evaporate? And the answer is no. See, there's nothing in there. What needs to evaporate? And the answer is liquid water. So imagine that I've got a big droplet of water. That's liquid. Now that I have liquid, some of that liquid can go into vapor. Some of that vapor goes into liquid. So I'm going to ask you a pretty simple question, and I want you to think about what this really means, right? I know you're going to write it down, but I want your brain to be engaged. How do I change the amount of water vapor in a parcel of air? Condensation or evaporation? Evaporation is putting vapor into the air from liquid. Condensation is taking vapor out of the air and turning it into liquid. What do I need in order for condensation or evaporation to be taking place? And the answer is I need both vapor and liquid. I can't have a process going from one to another without both of those there. If vapor starts to condense, what am I left with? Liquid. So I've got vapor and I've got liquid. If I have something evaporating, then what's evaporating? Liquid. I've got to have liquid. Now, how do I know that I have vapor in the air? I don't know. I can't see it. So what I'm going to say to you is, how do I know if I have water vapor in the air? I just always do. I've always got some. How much do I have? W, mixing ratio. Now, what I'm about to say is going to be a test question, so be aware of this. W is the exact amount of vapor that's in the air. W is the exact amount of water vapor that's in the air, okay? How do you change the amount of water vapor in the air? Evaporation or condensation. What do I need for those two things to be taking place? Liquid and vapor. How do I know I have vapor in the air? Well, I just do. How much do I have? W. How do I know if I have liquid in the air? Well, if there's liquid in the air, I can see it. And what do we call liquid that I can see that's in the air? Now, this is not, how do I see liquid on the ground? I could see a puddle. I could see an ocean. I could see a lake. I could see a river. That's water on the surface. Okay? How do I see water in the air? And the answer is, it's a cloud. So I get air, I get a cloud, which tells me I've got liquid water droplets. And that's what a cloud is. It's a bunch of real little liquid water droplets all suspended in the air. Okay? Now, let's go back to this picture. And this time I want to imagine that I've got a little puddle in this. Oh, this is, I don't need this one. Let's go to just a pen. I've got a little puddle of water over here, okay, on the bottom of the box. Okay, that's just water slopping around the bottom. Now, do you understand that there is a point where some of this water starts to evaporate? And some of these vapor molecules are going to come in contact with the water, and there's going to be condensation. Okay, so that's what's going on. There's vapor turning into liquid, liquid turning into vapor. When that amount of condensation and evaporation are the same, we say that the air is saturated. So saturation is when the rate of evaporation and condensation are the same. Okay? That's what we mean by saturated. So if you've done the module, that amount of saturation is called relative humidity. Saturation is when the relative humidity is 100%. Okay? That's what's really going on. And that's with the puddle. In the atmosphere, it's a little bit more difficult to understand that. You get more than 100% relative humidity, way beyond the scope of this class. So if you take another meteorology, you know what I'm talking about. If not, this is good enough. Vapor turning into liquid, liquid turning into vapor, goes back and forth, and then we say the air is saturated. There cannot be any more vapor than there is. So what I need to do is I need to say what relative humidity is. RH, which is relative humidity, is the amount of water vapor in the air. And I'm going to do this way because I think I can make it a little bit better. This is a fraction divided by the amount of water vapor that can be in the air. So relative humidity is the amount of water vapor that's in the air divided by how much water vapor can be in the air, right? So look, imagine this. Imagine in this box that the rates of evaporation and condensation are the same. Every time a molecule wants to come out into the air, some of those molecules go back into liquid. I can't put any more vapor in the air because the more I do, the more that comes out. So we are going to call that bottom number W with the subscript S, which is saturation mixing ratio. That's what saturation mixing ratio is, W sub S. So when it's just W, that's mixing ratio. That's how much water vapor is in the air. And keep in mind, what did I say? It's the exact amount of water vapor. It's the best way to answer the question, how much water vapor is in the air? Well, there's W. W sub S is how much could there be? Now, I want you to think about this. Look in the box, and the molecules are going like this. And these molecules are trying to get out of the water. Well, how do you get water vapor out of water? Well, you add heat to it. See, if I were to heat this water, wouldn't I start to boil it, or it would start to go into the atmosphere? So for instance, imagine this. Imagine I take some water, I sprinkled water on the ground. Do you understand that water will eventually go away? Where did it go? It went into the atmosphere. Here's the deal. If I want the amount of evaporation and condensation to be the same, that's saturation. What if I want evaporation to be more? In other words, have a greater rate of evaporation? Well, I make it warmer. Warm temperature is the fact that the molecule is going to move faster. So write this down. The warmer the temperature, the more water vapor that can be in the air. The more water vapor that can be in the air. So temperature goes up, the amount of vapor that can be there goes up also. Okay? Which means warmer temperatures can have more water vapor in the air. Now, what does that look like? All right, now we're going to go to someplace a little bit different. And I want you to imagine, rather than this, so I'm going to erase this now, and I want to do something like this. I'm going to imagine that I have a theater, and in this theater, I've got 10 chairs. Okay? They should all be about the same size, but whatever, right? So I got 10 chairs in this theater. Now, if I asked you how many people can be in the theater, what you'd be saying is that, well, there should be 10 people in the theater. There can be. That is W sub S. W sub S is 10 grams per kilogram, let's say. But it says how much could be there. Now, how many people are in this theater? Well, right now, there's nobody sitting in those chairs. They're empty chairs. I could have 10 people. So let's imagine this. Let's imagine that I go 1, 2, 3, 4, 5, 6. How many people are in my theater? The answer is 6. How many people could be in my theater? Well, 10. So what's my relative humidity? I have 6. I could have 10. 6 divided by 10 is 60%. So the relative humidity would be saying W is the number of people. How much water vapor is actually there? The number of people in the chairs. W sub S is the capacity. The capacity is 10. That's how many chairs there are. So here's an interesting question, and maybe you should write this down. How do I fill the theater? How do I fill the theater? Now, there's 2 answers to that, and you may not be thinking of this correctly, but I'm going to go ahead and just kind of talk about that for a second. How do you fill the theater? And the answer is I fill the theater by either putting more people in there or I take out the empty seats. And that's really what's happening in the atmosphere. I'm going to take out the empty seats. So watch this. I have 6 people sitting in 10 chairs. and I remove 2 chairs. I lower the capacity. Now I have 6 people sitting in 8 chairs. My relative humidity was 60%. Now what is it? 75%. Oh. What if I took out another chair? Now I have 6 people sitting in 7 chairs. Okay? And if I take out one more, I'm now full. I have 6 people sitting in 6 chairs. So this is where the mathematics, and really guys, this is not hard mathematics here. Relative humidity is equal to W over W S. Okay, so I can draw this in here and just go, that's what the fraction is. So W is how many people are there. Notice when I took out seats, did I lose people? So this number stayed the same. What changed? W sub S got the capacity. Remember, W sub S, saturation mixing ratio, how much can be there, that's a measure of capacity. That went down. Huh, interesting, huh? That went down. What did the relative humidity do? Well, it started out at 60%, now it ended up at 100%. So this went up. So the idea is this, let me do it this way, stayed the same. This went down, and this goes up. That means the capacity and the relative humidity are inversely proportional. One goes down, the other goes up. Okay? Inversely proportional is what you call that. So let's change this whole concept now for a second. And let's imagine that I have air, and this time this is not a chair, this is a box of air. What's in the box? Gases. What kind of gases? Nitrogen, oxygen, and water vapor. If I said to you, and I will think this way all the time, how much water vapor is in the box? You would say, well, there's some. And I'd say, well, how much is some? And you'd go W, there's W. How much could be in there? Oh, I don't know. Do you know what determines how much vapor can be in the air? Temperature. So do you agree that this box has some temperature? Sure. It has some capacity. I don't know what it is. It's something. It has some amount, W. Do you see a cloud in the box? No. Do you see the vapor? No, it's invisible. Do I have vapor in it? Yeah, I'm just going to assume so. How much? W. But it's not saturated. So I know that the relative humidity must be less than 100%. Now what I'm going to do is I'm going to take this box and I'm going to lift the box. And you remember what happens when you lift the box? The first thing, pressure decreases. The second thing, the box expands. Third thing, and here's the key, the temperature of this box gets colder. So this box up here is going to get larger, but it's going to be colder. Now, as it gets colder, what happens to the capacity? The capacity gets less. Like me removing seats. But what kind of seats did I remove? The answer is empty seats. What happens to the amount of water vapor that's in the box? Well, for a while it stays the same. Notice, nobody had to leave. Now eventually, let's imagine that to start with, I had 6 grams of vapor per kilogram of dry air in the box. But I could have had 10. What's my relative humidity? 6 out of 10, 60%. I lift the box, and now W, 6, there's still 6 grams of water vapor in there. I didn't take any out, put any in. But the temperature got colder, which means the capacity, W sub S, goes down. So now it's 6 over 8. That's 75%. If I continue lifting the box, I continue removing empty seats, and now I've got 6/6. What is happening? The relative humidity's gone up to 100%, and now we say the air is saturated. Okay? If I were to lift this box any further, any additional lifting, and that's going to make this box larger still and cooler. Oh, that's not a box, that's a bubble. Let's draw a box. Okay, so the box keeps expanding. What is the temperature doing? Well, it keeps getting cooler. If it gets cooler, what happens to capacity? It goes away. So what do I need to do? I need to take away a chair. Where's this person? Do they have a place? The answer is no. So I have to get rid of this thing. Well, getting rid of vapor is called condensation. So what forms within this box? A cloud. So the cloud is where water vapor first starts to condense. Now what that means is we have what's known as the LCL, I can make that a little larger, which is called the lifting condensation level. And the lifting condensation level is the base of a cloud, where the cloud begins to form. Okay, that's what the LCL is. So, gee, I wonder if this is important. I think it's really important. So let me go over here and let's just kind of review this again. And you need to do this on your own. You need to go back and take really good notes, because this is like how things in the atmosphere work. We all live on a planet with an atmosphere. This is what happens around us every day. Okay? So I have air. I lift the air. The air pressure goes down, the air expands, and the temperatures drop. Now, what rate does the temperature drop? And the answer is 10 degrees Celsius per kilometer. That's the dry adiabatic lapse rate. How much water vapor is in the air to begin with? Oh, I don't know, some amount, W. How much could it have? I don't know, some amount, W sub S. What determines that W subscript S? Temperature. Okay, so if the temperature goes down, what does W sub S do? It goes down. Look over there. What is relative humidity doing? It's going up. Eventually, the relative humidity hits to be 100%. We say that the air is saturated. The air has as much water vapor as it can possibly have. If I continue to lift the air, that box continues to have a lower pressure, it expands and cools, and this time that cooling results in a drop in the capacity, which forces water vapor to turn into liquid. Water vapor condenses. Okay? And therefore, the air stays saturated, the relative humidity is the same, but W goes down and so does W sub S. I'm condensing water vapor, and that's what a cloud is. Now, where does that start? It starts at the LCL. Woo! Nelly, if you were in my class, we would be repeating stuff. I would be testing you on this and quizzing you on it, but this is online, which means you still have to do the same things that I would do. You just have to do it on your own. This is why teaching in class is better than online. But you got to figure this out, okay? Now, so I'm going to erase all this stuff, and I'm going to give you one other really important thing. If I take water and I add heat to it, what do I get? I get vapor. Okay. So that's, oops, I don't know. That is taking liquid water and making it turn to vapor requires heat. That kind of heat for evaporation is called latent. That is latent heat. Latent is a word that means hidden. So you'll understand why it's hidden in a second. But do you agree that if I took water and I added heat to it, which causes evaporation, I am taking heat away? Now, if you were in my class, I would do this. You're at home, so you have washed hands, whatever. I'm not afraid. I'm going to lick my hand. Okay, I lick my hand. It's now wet. Now watch. I blow on it. When I blow on it, what do I feel? It's cool. Well, why is that? What I'm doing is I'm taking the liquid water that's on my hand and it's causing it to evaporation. And that results in cooling. It takes heat. Where's the heat coming from? My body. This is why we sweat. We sweat when we're hot. And when we put water on our skin, the wind blows, we do this, we fan ourselves, we are causing the water to evaporate, and it is removing heat. So evaporation results in cooling. You got to know this. Oh my gosh, do you need to know this? Evaporation results in cooling. When it rains, if it's in a cloud, it's not going to evaporate because the cloud's saturated. There's no place for the water vapor to go. But once it drops below the cloud, that water starts to evaporate. Evaporation results in cooling. And so what happens is that cool air comes down, mass convergence, mass divergence, mass continuity says as the cold air comes down, it spreads out, and you feel that cold air come and hit your face. That cooling from a thunderstorm or from when it rains is a result of evaporative cooling. But the opposite of this is true as well. That's not what I wanted to do. I want to go. It goes the opposite way as well. If you go from vapor to liquid water, which is called condensation, the heat is given back. Okay? So what does that mean? And I'm only going to say this once or twice. I can't underscore how important this is. But because it's on tape, you have to go back and make sure you understand this. And this is what I'm concerned about with online teaching. I can give you information. How do you process that information? I'm not sure how you're doing. I get no feedback from you. I give you questions, I give you thought, you take notes on it, but really, I want your brain to figure this out. I take a box of air, I lift it. First thing that happens, the pressure goes down, the box expands, the air cools, dry adiabatically, 10 degrees Celsius per kilometer. Eventually, I reach LCL, I reach saturation, clouds form. If I lift air high enough, clouds will eventually form. At this point, I continue to lift the air, the pressure continues to decrease, the box expands, it continues to cool, but it wants to cool at 10 degrees Celsius per kilometer. But at the same time it's cooling, what's going on inside the box? Vapor is turning into liquid. Water vapor condenses. But what's being released? And the answer is latent heat. So latent heat is being released. Where is it released? It's still adiabatic. It means without heat. It's not outside of the box. Heat is inside the box. So at the same time it wants to cool, it's now also getting warmed by the release of latent heat. And what that means is that when I get to the LCL, when I get to the lifting condensation level, to the base of the cloud, that air will now cool at a slower rate. It wants to cool dry adiabatically 10 degrees Celsius per kilometer, but because there's heat being released at the same time, hidden within the box, it now cools at a slower rate. It cools at a lapse rate of 10, now it's less than 10. It cools at a slower lapse rate. Guess what we call that? That's the wet adiabatic lapse rate. Now, the number is not important for you in this class, but what you need to know is this. When you're in a cloud, air going up will cool at a slower rate than the dry adiabatic lapse rate. Numbers that are less than 10. Okay? And that's what's going on. Now, the opposite is all true. If air comes down, it's compressed, and then it gets warmer adiabatically. But this is what's going on in the cloud. is that the heat in the cloud is changing the temperature because I'm heating it. The cloud is the parcel. Okay, now let's go back to this. Here we are back in this video, and we're going to talk about a couple things. So here's stuff that you can read on your own. And then says, well, let's deal with other terms. One of those terms is called the wet bulb. Say what this wet bulb is, it's a result of something called a sling psychrometer. This is what a sling psychrometer is. It says download video, so please do that. Notice that there's one thermometer just sitting there. You spin it around, and it's the temperature. It's the dry bulb, whatever, the temperature. But on this one, see this little wrapping of cloth? That wrapping of cloth you soak in water. So when I spin it around, what does the water do? It evaporates, just like you sweat. By the way, a little funny joke. If I said, if you're sweating bad, oh, I'm sweating like a what? What do we use as an analogy? Two things. I'm sweating like a pig, or maybe I'm sweating like a dog. Do you know that pigs and dogs don't sweat? Dogs don't sweat. Dogs pant and evaporate water in their mouth. Pigs don't sweat, so they roll around in mud to keep themselves cool. We sweat, which is great, so that when it's warm, that water evaporates and cools. When will it cool more? When I fan it or on a really dry day? See, when the relative humidity is really low, it evaporates quick and I feel better. If it's really humid out, then the water doesn't evaporate so quickly and I don't get cooling. So what does your body do? Well, I'm hot, so it starts sweating, but it's not cooling. So what do? I put more water on my skin. I sweat more and more. And so what you're doing is you're dehydrating. Your body's trying to cool you down. It's not evaporating, and therefore you're not cooling. And that's why in a hot, humid day, it's really easy to dehydrate. And we'll talk about some of those things next week on the next lecture. Okay, so that's called the wet bulb temperature. It just measures the effective evaporation. The drier it is, the lower the wet bulb temperature. Now there's something else here called the dew point, and this is a little bit different. So this is so important. I want you to know the exact definition I want you to have. The temperature to which air must cool at constant pressure in order to reach saturation. Okay, that is what something is called the dew point. And oftentimes we will say the dew point is T with the little subscript D. That's called the dew point temperature. And I should spell which correctly, but get over it. Okay, so the dew point is not what we're doing when we lift air, because do you agree that the air is exchanging its pressure? The dew point is like sitting around at night. So imagine, let's say one day, and I can even show you this. I can say, well, here's the current conditions at COD right now. The temperature is 74, and the dew point is 50. Okay? What I'm saying is that tonight, when the temperature drops, if the temperature were to drop to 50 degrees, the air would become saturated. Now, that doesn't usually happen over a large area, but if it did, it would be foggy. But if it cools right on the ground, and if you've ever walked barefoot in the summer, you know that the ground can be really cold by your toes, even though your face is not so cold. So instead, you get dew to form. Just like if you had a can of Coke and it's cold, the water vapor in the air is cooling in contact with that aluminum can, and the temperature drops and you get condensation. That's dew. Dew forms on the can. So the dew point is super important. Now, the best measure of water vapor in the air is W. It's an exact amount. Dew point is really helpful. And the reason dew point is helpful is because it tells me what I'm going to feel in terms of comfort. So I'm going to go to something here. I'll go ahead and show you this. Here is the current dew points across the United States. And I'm going to hide this for a second. In purple, the dew points are in the 70s. Okay, when the dew point's in the 70s, you're going to say, oh my gosh, it is so muggy, it is so, you'd say humid, but you'd be wrong. But that's what you'd say. You'd say, oh, it's so humid, it's ugh. The dew point in the 70s is how you feel, it's horrible. The dew point in the 60s, you'd be like, it's kind of humid. You're okay, but you can definitely feel like it's humid. The dew points drop into the 50s, and you kind of go, wow, that's really comfortable. Anytime the dew point's in the 50s, no matter what the temperature is, you're probably like, that's pretty nice out. Now over here in the West, the dew points are in the 20s, or even single digits, double digits, 12. There might be some later on in the desert, but that's a desert. The dew points are really low. And that's why in a desert you go, it's so hot. Right up here, it's even lower, or it's low, but it's not as low as in the desert. So if I look at the forecast for the next few days, I see dew points here in Chicago being in the 30s. But then look at this, it gets much cooler. And that cooling is going to be really cool nights because now the temperature can drop below the dew point, or at least to the dew point. So it's going to be we're very dry air mass. Now what kind of a dry air mass? It's cool and dry. Oh, well that's continental polar. What kind of air mass is really humid? Well, that's maritime tropical. So when I look at something along those lines, that's what I'm seeing. The dew point is how I feel comfort-wise. So that's really helpful. The worst measure of moisture is relative humidity. And why is that? Okay. Well, we said this before, that when the temperature, let me do this. When the temperature goes up, ooh, that's not what I wanted. When the temperature goes up, and I'll draw a little arrow, what does W sub S do? W sub S goes down, and what does the relative humidity do? Hold on, I'm lying. I'm lying to you, please ignore that. The capacity goes up, right? Greater the capacity, greater the temperature, etc. What does relative humidity do? Relative humidity goes down. So let's say one day you wake up and it's 75 degrees and the dew point's 70, right? You're going to feel miserable. That's like, wow, it's really humid. And the relative humidity is going to be, I don't know, 84%. Now the day goes on and the temperature goes up into the 90s. You have 95 degrees with a dew point of 70. Do you know how awful that's going to feel to you? But what has the relative humidity done? It's gone down. It might be 40%. So relative humidity doesn't tell you how you feel. It tells you how fast water vapor can evaporate. Dew point is what tells you how you feel. So really the worst thing to determine moisture content is relative humidity. The best thing is W. Dew point tells you something about how you feel in terms of comfort. The only thing that relative humidity is good for is to determine how fast things evaporate. So when we get into fire weather, we want low relative humidities because any water is going to evaporate really quickly and dry things out. Okay, so that's what that is. So that's what those are. Now there's a discussion on relative humidity. I would suggest that you need to do these questions. They're super important. Do not skip over them. Here's temperature relative humidity relationships. And they talk a little bit about this. And again, boy, this is important. Do you understand what we have here? We have the temperature going down, going up, going down. Right? What is this up and down nature of the temperature called? That's the diurnal variation. What is the relative humidity doing? The relative humidity goes up when the temperature goes down. It goes down when the temperature goes up. and it goes up when the temperature goes down. So do you see this? That relative temperature are going in opposite directions in that diurnal swing. So if fires are going to be worse when the relative humidity is the lowest, what time of the day will fires burn the best? In the warmest time of the day, 6 hours before or afternoon. When will it be best? When will it burn the least quickly? When it's coolest. So all of that is what this is all leading to, trying to understand this. Go ahead and erase that. So temperature changes, we talk about this. This should now make more sense to you. So I want you to do all these questions. I'd like you to put some of this in here. This is important to really check your understanding. So put this in your notes. Answer those. Now the rest of this stuff is just reading charts. So I have blue as the dew point, RH is the relative humidity, and I'm given the temperature and the wet bulb temperature. And you use this, the dry bulb temperature is 40, the wet bulb temperature is 34, I go here. If that's the case, the relative humidity is 58, the dew point is 27. Now you don't have to take notes on this. This is just use these charts to answer the questions for the quiz. So remember, this is a sling psychrometer. That's the name of this. So here's the word, here's how you spell sling psychrometer. That's this instrument. It's really easy to measure this thing if you spin it around. And then from that and these tables, I tell you the relative humidity of the dew point. That's all they're saying in this thing. Now local effects, we've talked about this in terms of slope aspects, so please take a look through this. It talks about why fire might be different times of the day, so read through this. Vegetation, this should make sense to you, okay? So the warmest temperatures and the lowest relative humidity at nighttime are at the ground. That's why you kind of stay underneath trees. It'll keep it kind of warmer at night. Wind mixes it up. We'll eventually deal with more of these when we get into the fire weather. Here they're talking about air masses, okay? You've already done this twice in your notes. You don't need to do it a third time here. But again, you should know about what these air masses. Do it by way of review. What kind of air masses do you think are worse on fires? Well, continental tropical, hot and dry. Hot and dry, low relative humidities. Okay, and then here's your summary. That would be a good thing to have. There's your inverse proportion, and then just kind of repeat it, and there you have it. Okay, so super important, all these things. And if I were in class, I would review it with you. Like tomorrow, we're going to get together and do this again. You have the information. You go back and do your own review. If you don't understand what I mean by something, write me about it, okay? So everything on the first 2 weeks up through here on the third week will be covered on the test, okay? Again, open notes. Once you start, you have to complete the test, okay? And it's timed. So all I ask you to do is work alone, but feel free to look at your notes. And if you don't find them in your notes, what that tells me is you're not taking good notes, okay? It's not gonna be a super easy test, but you should be able to go, gosh, I know this. Study your notes, get prepared, and then take the test. Okay, if you have any questions, contact me. I'm gonna stop sharing. Like these clouds back here, notice the air has gotten to the LCL, and that's why you get base of clouds, and I can see that. That's liquid water. Okay, guys, you have a great week, and we'll talk to you later.